So in this problem, we're told that an open organ pipe is being designed to have fundamental frequency of nu equals 256 Hertz, which is middle C. And we're asked, first, what is the length of this pipe going to have to be? Now in order to calculate this, I'm going to calculate what the wavelength of sound that is emitted from the pipe has to be, and then fit that wavelength to the fundamental frequency of an open tube. So first of all, we know that nu times lambda has to be equal to the speed of sound, which is 330 meters per second. This tells us that lambda is equal to v sub s divided by nu, which is 330 meters per second divided by 256 hertz, which is equal to 1.29 meters. So now, of course, we have to fit this to an open tube. Fundamental frequency has n equal to 1, and since sound must reach an antinode of pressure, a node of pressure on both open ends, because it has to be equal to the outside pressure, we know that we can draw the pressure of the wave like this, which gives us that L is equal to lambda divided by 2, because the sound completes one full wavelength in an oscillation back and forth across the length of the tube. So this tells us that L is equal to 1.29 meters divided by 2, or 0.645 meters. Now in part B, we're asked to find the fundamental frequencies, the frequencies of the first and second harmonics of this tube. So all that means is that we take n equal to 2. That gives us a sound pressure graph that looks something like this, where we have antinodes 1/3 of the way and 2/3 of the way along, and nodes at both endpoints and the midpoint. This tells us that lambda is equal to L, and we can go back over to this equation, and we find that nu is equal to v sub s over lambda. We know that lambda is L, so v sub s over L is equal to 330 meters per second divided by 0.645 meters. But remember, 0.645 is just 1.29 divided by 2, so we end up just getting 512 hertz. And this relationship is going to hold for all open tubes. If you take the first harmonic, you're just going to double the frequency. And the same pattern holds for n equals 3. For n equals 3, we add one more antinode along the way. So we now have antinodes at each quarter point and nodes at each third point. We again know that nu is equal to v sub s over lambda. This time, lambda is equal to 3L over 2, 2L over 3. And so we get, for our, the frequency of our second harmonic is going to be 768 hertz, which is, of course, just 256 hertz times 3. Now, finally, for part C, we're asked what the new fundamental frequency would be if at some later point in time, one half of the tube was closed. So for an open closed tube, we know there has to be a node on the open end and an antinode on the closed end, because the pressure is going to build up at the closed end. So the fundamental frequency is just going to be this pressure graph right here, where we have that lambda is equal to 4 times L. So this allows us to, again, calculate the frequency. Nu is equal to v sub s over lambda is equal to v sub s over 4L is equal to, and that's just going to be half of the original frequency. So 330 meters per second divided by 2.58 meters is just one half of that, so 128 hertz. And so here we have the length of the tube that will generate a fundamental frequency of 256 hertz, the frequencies of the first and second harmonics, and the frequency if we were to close one end of the tube.